2, we're going to talk about molecular nomenclature, bonds, and shape. Right? So we're going to do 3 bullet points, but this is the part we're going to talk about in this video. Okay? Please read sections 12.3, 12.8, 12.9, and 12.10. This is about electronegativity, so it's really important that you read that one. And then these are about shape, and so it's really important. Imagine that. Okay. There's a self-check exercise 12.5. Just do letters C, D, and F from page 369. But after you do this, after you do the video. Okay, so we talked about covalent bonding. Sharing electrons. Look at all that sharing going on. It's between two nonmetals, and sometimes we refer to them as directional covalent bonds because the electrons that they share are then centered or centralized between the two atoms. Okay. Now, you saw this in the lab. What kind of properties might you observe if covalent bonding is present? Well, you might notice it's made of the compounds are made of nonmetals, or the elements are nonmetal elements. They don't conduct electricity. They have variable melting and boiling points, but they're the only type of compound that has relatively low melting and boiling points. They're only a polar version of covalently bonded molecules will dissolve in water, and many are insoluble in water. They have strong bonds that hold the atoms together, but then the strength of force between one molecule and another molecule can vary. So let's see what we would call some of these molecules. So we're looking at compounds that have two nonmetals in them. The first element of the two nonmetals we always have to use a prefix for unless there's only one. The second element of molecular compounds will always have a prefix. And the second word of a molecular compound will always end in IDE. So you need to memorize these prefixes and use them when you have one of something. Dis when you have two, tris 3, tetras 4, 5, hexa and hepta. Heptas might not be as common, octa, nona, and deca. So I'm guessing you knew several of these based on geometry. But you need to memorize these prefixes, and now let's practice. CO is two nonmetals. This is a compound called carbon monoxide. Okay, this could be your guide. So, first word needs a prefix unless there's only one. All right, so we don't have, say, monocarbon because you don't need a prefix when there's only one of the first element. Monoxide, always prefix on the second, and then no double O's, so it's not monoxide, it's carbon monoxide. So look, it's two nonmetals, so we'll call it sulfur, and we don't need a prefix because it's mono for the first. And then 6 is hexa. How many? Hexafluoride. You change the end of the fluorine to IDE. And there we go, phosphorus. And then 5 chlorines is pentachloride. Phosphorus pentachloride. All right. A little crazy. I know noble gases don't form bonds, but we have forced them to. And there's 2, so we need a prefix. The only time you can skip a prefix is if it's mono on the first. So diazenon, octa, bromide. Notice I'm just following the rules. All right. I want you to try that one. Try nitrogen. So we have N, and there's 3 of them. Monosulfide. So there's one of the element that comes from with the IDE ending. So S, right? Hexasulfur, so 6 S's. Dichloride, Cl2. And then I want you to try that one. All right. When we talk about why these bonds form in the first place, we have to talk about electronegativity. Fortunately, you memorize the trend in electronegativity and hopefully know the definition is ability to pull electrons. Ability to pull on bonded electrons. So attracting bonded electrons. So 2 atoms will have different electronegativities unless they're the same atom. So if the electronegativity difference between the 2 atoms is 0, then neither of them will pull on the electrons more than the other. That's going to be a covalent nonpolar bond because the electrons are shared equally. So here's a model of that. If the difference is pretty small, is a little bit bigger, then they're going to have covalent bonds again sharing electrons. And they're going to be polar, which means that even though they're sharing electrons, they're unequally sharing them. So instead of an even distribution of electrons, it's going to be an uneven distribution where the more electronegative atom more electronegative atom pulls the electrons that are being shared towards its side of the bond, so it's kind of negative and kind of positive on the other side. If the electronegativity difference is huge, I'll tell you, you're going to get an ionic bond. An ionic bond, the electrons are actually transferred from the less electronegative to the more electronegative. And you get a different kind of bond than what we're seeing in this unit. Okay, so here is a table of electronegativities. So where are the biggest differences? Well, here's the most electronegative. Here are the least electronegatives. So that's where ionic bonds are going to form between metals and nonmetals. But we're talking about covalent bonds, which are mostly nonmetals. Okay, and notice their electronegativities are all sort of big, so the difference between them is going to be kind of small. Right? So molecular compounds or covalent bonds involve sharing electrons. Right? So this is just in words what happens to go from covalent to ionic. This is electronegativity difference. Okay, electronegativity difference. So you subtract the electronegativities, and if there's a small difference, then they're going to be nonpolar, no poles or differences. Okay, if you subtract the difference in electronegativities and you see a kind of medium difference, somewhere between 0.5 and 1.9, then there'll be a polarity in the bond, but still shared electrons. And then a huge difference is ion. So let's look at N and O. So here's N and here's O. What's the diff? It's 3.0, 3.5. The difference is 0.5. That's going to be a polar covalent bond because it falls into that category. So all you have to do is subtract the electronegativities, look at the difference, its absolute value, right? And so let's just do C and H. There's a couple other ones you can try. So we got 2.5 and 2.1. And so the difference is 0.4. So that's non-polar covalent bond. Okay, so part of what we can talk about molecules with is their shape. So many of the properties of covalent molecules can be explained if we understand the shape of the molecule, and then we can understand the polarity of the whole molecule. So let's look at some dot structures. All right, once you look at the dot structure for a compound, you count how many areas of electrons are on the central atom. 1, 2, 3, 4 areas. 1, 2, 3, 4 areas. 1, 2, 3, 4 areas. So all of these have 4 areas of electrons around the central atom. The VSEPR theory we use to predict these shapes tells us that electrons are in pairs, and those pairs push away from each other because electrons are negative. And because they push away from each other, they spread out, and that's going to tell us the shape. Okay, so again, those 4 pairs of electrons around those central atoms are going to be spread out as far apart as possible. And the shape that you get when 4 pairs of electrons spreads out is a tetrahedral. So here's when CH4 has 4 bonds. So those bonds are going to be spread out as far apart as possible, and this is going to be called a tetrahedral. Well, NH3 also has 4 sets of electron density around the nucleus, around the central atom. Sorry, he meant to say central atom. 1, 2, 3, 4. So this kind of looks like a tetrahedral. But guess what? Lone pairs are invisible. So we can't see that lone pair at the top. But because it's there, it's going to make a pyramid shape. Okay. Again, with water, there's 1, 2, 3, 4 pairs, 4 sets of electrons around the central atom. And so everyone needs its own space. So it kind of looks like a tetrahedral, but lone pairs are invisible. We can't see those. And so this is going to be the shape of the water molecule. So there's 3 names for the shapes, but all these shapes are formed because of 4 areas of electrons around the central atom. And so here's another name of a shape. The shape is called linear. Why is it called linear? Because there's 2 sets of electron density around the center atom. So they spread out 180 degrees and you get a linear shape. These are called trigonoplanar and bent, but let's see why. Here's the dot structure for BF3. Remember, this is an exception to the octet rule, so it only has 3 areas of electrons around the center atom. Spread those far apart as possible, you get a flat triangle. Boom, boom, boom. Flat, though, trigonoplanar. Okay. This also has 1, 2, 3 areas of electrons around the central atom. So you spread that out, and there's a lone pair up there, but guess what? Lone pairs are invisible. And so this is called a bent shape molecule. Okay. Wow. What if we have 5 areas of electrons around central atom? Okay. All of these have 5 areas, but this is all atoms, so it's called trigonal bipyramidal. This is 4 atoms in a lone pair, so it's called a seesaw shape. Okay, this has 3 bonds and 2 lone pairs, so it's called T-shape. T-shape. Okay. All right. Here are the big ones. The octahedral has 6 pairs of electrons around the central atom, and so they spread out as far as possible, and you get your octahedral. This has 1, 2, 3, 4, 5, 6 areas of electrons around the central atom, and it could be in resonance, interestingly enough, right? But either way you draw it, there's a lone pair on xenon, so there's a lone pair, but it's invisible, you can't see it, so it's a square parameter. All right, to review, molecules have shapes, okay? And those shapes are determined by the pairs of electrons around the central atom. So know the electron pair arrangement, and then the shape, after all of those pairs of electrons spread out, is what you see with all of those pairs of electrons spread out. But you can't see lone pairs, but they cause the shape. Okay? Here are the kinds of shapes you might be seeing with molecules. And then in the next video, woohoo, something to come, we'll be able to look at those shapes and decide if the molecules are polar or non-polar. Okay? Please do read these sections in the book. All right? And do self-check 12.5 on page 369. Just see D and F. Right? All right, so hopefully you can tell the name of a molecular compound, use those prefixes, and vice versa. You can tell the difference between a polar and a nonpolar bond based on electronegativity differences. And then, because of the shapes of molecules, we'll be able to talk about the properties. Well, we know the properties of covalently bonded molecules, but the shapes are going to lead us into what we can tell about them. So, peace out. Thanks for playing.